this superposition of causal structures as a universal resource. So traditionally, what when we are when in quantum mechanics, the causal order of events are taken to be finite. So say we have two events A and B, and the causal order, whether A is in past of B or future of B, that is well defined. But recently, there have been studies which take this causal order of two events or multiple events to be indefinite, in the sense that suppose system prepared in a system prepared in the spin state, say up plus down, up z plus down z, then the Sx component is indefinite. In the same sense, indefinite causal order has been studied. And this talk that I will be giving will be is based on this recent paper that we have published in Physical Review by the same title. And this work is in collaboration with Orkoprabha Ghosal, Devorshi Das, Anando Maiti. So this is the plan of my talk. First, I will define what you mean by events, causal order, and how indefinite causal structure can arise in a quantum gravity scenario. Next, I will define what we mean by non-local quantum operations, their local implementation, and the role of resource in that. Finally, I will discuss about the role of indefinite causal structure as a resource, and then I'll conclude. So when we say, suppose some event like the India-Australia cricket match is taking place. So when I say that this is an event, then the natural two questions that come is where it is happening and when it is happening. So to completely define an event, we need to mention its location and its time. This is the physical definition of an event, and mathematically it is represented by a point in a manifold, in a space-time manifold, and it has four coordinates: time and the three spatial coordinates. Now consider these two events x1 and x2, which are defined in some, which has their four coordinates individually, and these given these two events, we can define a causal relation between them. If, for example, a light beam starting from an event x1 reaches event x2, if it is possible that a light beam sent from x1 reaches x2, then we'll call that x1 is in causal past of event x2. On the other hand, if an light ray emitted from event x2 reaches event x1, then we'll call that event x1 is in the causal future of event x2. So these two causal relations are mutually exclusive. I mean, if event x1 is in causal past of event x2, then it cannot be in its causal future. And these two relations are called causally connected. So there exists a relation between two events x1 and x2 such that these things can happen. On the other hand, if two events are such that it is neither possible to send a light signal from one event to the another in any way possible, in any route it's possible, then we'll call that these two events are causally disconnected or they are space-like separate. Now, according to general relativity, it is in general relativity we see that causal structure of a space-time is determined by the geometry of the space-time. So what do you mean by causal structure? Causal structure defines the causal relation between each and every pair of points, each and every pair of events in the space-time. And that is determined by the geometry of the space-time, which is given by the metric of the space-time. And from Einstein's field equation, we can get the geometry of the space-time from the matter energy distribution of the matter energy distribution in the space-time. So if we consider the matter sector, that is this T mu nu is the stress energy tensor of the matter part, and that determines the G mu nu. And R mu nu and R are basically some function of higher order derivatives of G mu nu. Now, if we consider the matter to be classical, then the metric that we get is also classical. I mean, it is classically deterministic. So once we have a classical matter, our metric is fixed. So let's say this is a mass which is located in this region, and correspondingly it creates a warp in the space-time manifold, and this warp is described by this mu metric. On the other hand, if the mass is located somewhere else, then the metric that is produced is g tilde mu nu, and this metric are totally different. This is there uh, in terms of general relativity, they are called diffeomorphism invariant. Diffeomorphically not connected. They are not diffeomorphically connected. However, if we consider a quantum mass, so what do you mean a quantum mass? So the matter, the mass is situated in a superposition of both the two locations. So it is situated here as well as here in the superposition sense. Then the metric that is produced for the space-time can also be thought of as in a kind of superposition. Now this ket g mu nu and ket tilde g mu nu it has to is not to be taken literally, because the Hilbert space or the quantum mechanical language of the space-time of a quantum gravity is not well established till now. So we are taking it in only in a say pedagogical sense. Now, so we see that given the mass is in a quantum superposition of these two space-time, we get the mass is in quantum superposition of two location. The metric may lie in a quantum superposition, and as we have mentioned that metric determines the causal structure, we will get a indefinite causal structure of the space-time. Now we'll discuss a very uh, concrete example where we'll see that this actually takes place. Now consider this scenario. The mass is located here, and consider two clocks, clock A and clock B, located such a way that clock A is located nearer to this mass and clock B is located further from that. Now we know and that a clock which is in nearer to a massive object, it ticks slowly. So a 1 second recorded by this clock is larger than the 1 second recorded by the clock B. So these dots are representing the ticks of the clock. Now if I define an event, say x, at the location of clock A and the time ta recording say 4 seconds. So this defines my event x. Similarly, I am defining an event y, which is defined at the location of clock b and tb equals 4 seconds. So these are my definition of the two events. And now since ta equals 4 second is occurring at a later instant than TB equals 4 seconds, it may be possible that a light signal emitted from the location of clock B reaches the location of clock A before TA equals 4 seconds. So in this case, we will have the event X to be in the causal future of event Y. Now let's take the reverse scenario, where the mass is now located nearer to the clock B. Now, since the mass is located near to clock B, the ticking rate of clock B is slower compared to the ticking rate of clock A. Now, if we define the same set of events, like say X defines the TA equals 4 seconds at the position of clock A, and TB equals 4 seconds at the position of clock B, it makes event Y, then it may be possible that a light signal emitted from from event X reaches event Y. So in this case, when the mass is located nearer to clock B, event Y is in causal future of event X. So in the previous case, event X was in causal future of event Y, and in this case, event X is in causal past of event Y. Now, if we take the scenario where where the mass is located in a superposition of of L and R, then the causal relation between X and Y becomes indefinite. We don't know which one is in the causal past of which one, and this gives rise to an indefinite causal order between the two events x and y, and it was first shown in this paper by Magdalena Zich in Nature Communication paper. And this is sometimes also referred to as the gravitational switch in the community. Now, let's move on to the next portion of the talk, which is the non-local quantum operations and quantum resources. So what we mean by quantum operation is are so quantum operations are basically completely positive maps that map an element from the density operator space of a Hilbert space to itself. We have taken the input Hilbert space and the output Hilbert space of the map to be same. So, so rho A belongs to the set of density operator of some Hilbert space H, and rho prime A also belongs to the same density operator space of the Hilbert space H, and phi E gives the transformation between rho A and rho A prime. And the characteristic property of phi is that it is completely positive. We can extend this definition for the case of multipartite quantum systems also, where now the Hilbert space can be factorized in terms of the number of parties. Now, when we define quantum operations for multipartite quantum system, we see that not all quantum operations are locally realizable. Only a subset of them are actually locally realizable. Now, what do you mean by locally realizable? So consider this scenario where say we consider a bipartite system such that one part of the system is in Alice's lab and the other part is in the Bob's lab. And Alice and Bob's lab are spatially separated. So they are not in the same lab. Alice can implement quantum operation only on her part of the subsystem. So Alice's quantum operation acts on the reduced subsystem of the entire state rho AB. Similarly, Bob can also implement quantum operation on his local subsystem, and they can communicate with each other via classical communicating device. Like they can exchange classical information between them. This sets the paradigm of local operations and classical communication, or LOCC for short. Now, the set of quantum operations that are implementable by following this protocol of LOCC are called actually locally realizable. Now, as I said, that not all quantum operations are locally realizable. That means that all quantum operations are not implementable by following this LOCC protocol. Let's see an example. Consider the rho AB, the state of the shared bipartite system is 0A tensor 0B. And they wish to implement the quantum operation such that the final state becomes an entangled state like alpha 00 plus beta 11. So this is the quantum operation that they are trying to implement is an entangling operation, and it is a very well established result by Horodecki and et al. That it is not possible to increase the entanglement of a bipartite system in a multipartite system by LOCC, because the entangling operation is a non-local operation. So those quantum operations which are not locally realizable are called non-local quantum operations. So this limitation of implementing the whole set of quantum operations by LOCC is also manifested in form of some non-local tasks which are not achievable by LOCC. For example, local state transformation, local state discrimination, swapping, etc. I will discuss one of these tasks in the later part of my talk. However, if Alice and Bob are supplied with some additional quantum resources, for example, entanglement, then they may be useful to implement larger subset of quantum operations than LOCC. And this motivates us to define what is called as universal resource. So given a quantum resource, if Alice and Bob can implement the whole set of quantum operations using that quantum resource, on arbitrary quantum state, then that resource is called universal resource. So the criteria is that Alice and Bob will be able to implement all non-local quantum operations and on arbitrary quantum state. They don't need to have the knowledge of what is the state of the shared system. And an example of this is that for if we consider say 2 cross D system, qubit cross qubit system, then it can be shown that 2 EBIT of entanglement is a universal resource. The explanation is very simple. Say if Alice and Bob share 2 bits of entanglement, Alice can say Alice has the qubit card. Alice can teleport her qubit to Bob's lab, and Bob can implement any desirable non-local quantum operation because both the system is in his lab, and he will transfer the state of the system to his any desirable state, and by the second entanglement, shared entanglement, he will be able to back teleport the state to Alice's lab. So from an initially shared bipartite state, we get a new bipartite state which is by implemented by the implementation of non-local operations. So 2-bit entanglement is a universal resource for city plus city systems. Now the question that we ask in this scenario is that, so we have seen that indefinite causal structure can arise due to the quantumness of the matter. So in the framework of indefinite causal structure, which class of quantum operations are locally realizable? The answer is that all class of quantum operations are locally realizable. Hence, we can conclude that this indefinite causal structure is a universal resource. And let's see how. So consider this framework. Here, just like the previous one, Alice and Bob is share a bipartite quantum system prepared in some state rho AB. They are able to implement LOCC operations. Furthermore, there is another agent, say Charlie, who is able to create a superposition of matter in this L plus R or L minus R form. So Charlie is able to create this kind of superposition of matter. Furthermore, Charlie is able to implement measurement on these masses. I mean, Charlie will be able to measure the state of the mass in L plus minus R or anything, any measurement that he wish. And Charlie also has a classical communicating device, and he can communicate his measurement outcomes or any information that he wish to convey to Alice and Bob. So this is a framework that we are going to deal. Now to utilize this indefinite causal structure. So since say Charlie has prepared the mass in L plus R configuration. Now the causal structure of the space time is now indefinite. Now how to utilize this indefinite causal structure as a resource? Let's look at that. So the protocol that we will follow is like this. Say for example that Alice wait for 4 seconds. If she receives a signal from Bob within these 4 seconds, she will implement quantum operation phi 2 on her subsystem. If she does not receive a signal from Bob within these 4 seconds, she will implement the operation phi 1 and send a signal to Bob. Bob will do the likewise. That means he will wait for 4 seconds. If he receives a signal from Alice, he will implement phi 2 on his subsystem. Otherwise, he will implement phi 1 and communicate to Alice. Charlie will measure after this protocol has been implemented. Charlie will measure the mass system in L plus minus R basis, and he will communicate the result to Alice and the measurement outcome. I will come to this later. So let's see how this protocol is useful to implement quantum operations of higher subset than LOCC. Suppose now let's revisit that entangling operation. Suppose Alice and Bob shared a product state 0 tends to 0b, and now the quantum operation that they choose is phi 1 sequence identity and phi 2 equals sigma x seed flip. So when the mass configuration is in L state, so this is corresponds to L state. L state means Alice's event will be in future of Bob's event. So Bob will not receive any signal from Alice, so he will implement phi 1, that is identity, on his subsystem, and he will send a signal to Alice which she will be able to receive because her event is in the future of Bob's event, and she will implement the bit flip operation. So this is due to the mass configuration L. Similarly, when the mass configuration in the R Bob's event will be in the future of Alice's event. So Alice will not be able to receive any signal from Bob, and she will implement the identity operator, and she will send a signal to Bob, and Bob will implement the bit flip. Finally, Charlie will measure the mass configuration in L plus minus R basis, and depending on his outcome, the Alice and Bob's state of the Alice and Bob shared system will be either of the two states, 0, 1, plus minus 1, 0. And it is a maximally entangled state after Alice and Bob has received the message from Charlie that which outcome has occurred in his lab. So we see that entangling operation is implementable by using indefinite causal structure following LOCC. So now, once Alice and Bob are able to create entanglement from starting from a pure product state, then they will be able to, it is evident that they will be able to implement higher subset of quantum operations than LOCC. But is this entanglement generation always necessary? Let's answer this question. Okay, so to establish that indefinite causal structure is a universal resource, we need to show that it is possible to teleport Alice's subsystem to Bob's lab and vice versa. So now let's consider this state that the Alice and Bob shared a random state in the dimension C2 cross C So Alice has a qubit and Bob has a qubit, and the state of the system is any arbitrary quantum state. Now, Bob also has an ancilla qubit in his position, which he may label by 0b prime. Now, in order to teleport, what Alice and Bob will follow is that Alice and Bob will run the set protocol on Alice's qubit subsystem and Bob's ancilla qubit, not on Bob's share of the qubit. Bob qubit share is not to be implemented. It will be implemented on Bob's ancilla qubit. And again they will choose the operation phi1 equals identity and phi2 equals bit flip. So what happens is that when L is the state of the mass, then Alice will implement the bit flip operation on her qubit subsystem, and Bob will do nothing on both his qubit ancilla and his qubit subsystem. And when the mass is in R state, Bob's event is in the future, and so Bob will implement the bit flip on his ancilla qubit. So 0 b prime turns to 1 b prime, and Bob's qubit subsystem is remain as it is. Alice will also implement identity. Now, Charlie will measure this mass configuration in plus minus basis and communicate his outcome to Alice and Bob. So when Charlie measure in the L plus minus R basis, we see that the Alice's A, B, and B prime will be a tripartite entanglement after Charlie's measurement. Then Alice will measure in 0, 1 basis and communicates to Bob. So he will disentangle her subsystem, and now the only B and B prime are entangled. So after receiving Charlie's outcome and Alice's outcome, Bob will do a necessary correction operation on his subsystem and to get the initial shared state entirely in his lab. So let's for say example, Charlie gets minus, say L minus R is the state of the mass, which is Charlie obtained, and say Alice has obtained 0 outcome. Then this will be the Bob's collapse state, B and D prime, and he will implement this quantum correction operation to obtain this initial shared state. So once Bob get the entire state initially shared between Alice and Bob, he will be able to implement any desirable quantum operation since it is entirely in his lab, and implement rho b prime b to rho prime b prime b. So he has implemented the quantum operation. Next, now one thing to note is that since Alice is measuring the mass in L plus minus R basis, the coherence of the mass is not lost. So the post measurement state of the mass is again give rise to the indefinite causal structure. The mass will again be in a superposition of the two location, and it will again give rise to indefinite causal structure. So using that indefinite causal structure, Bob will be able to back teleport the ancilla qubit state of the ancilla qubit to Alice's lab, where now instead of Alice doing the measurement in 0 1 basis, now Bob will implement the 0 1 measurement on the ancilla qubit. So now we will have rho prime b prime b to rho prime ab. So starting from any arbitrary quantum state rho ab, we can go to rho prime ab using the quantum operation. So these suggest that local operation and classical communication with the indefinite causal structure as a resource is sufficient to implement the entire set of quantum non-local quantum operations. So this is that for C2 cross City system, indefinite causal order of two events is the universal resource. Now, as we have mentioned that this this limitation of LOCC to implement the entire set of quantum operation gives rise to non-local tasks. One such task is the local state discrimination, and we'll show that in using indefinite causal structure, it is also possible to execute this non-local task. So let us consider the local state discrimination paradigm. The problem is, suppose we have a collection of four Bell states. D1 goes like 0, 0, 0 plus 1, 1, 0, 0 minus 1, 1, and these are the other four Bell states. Now, the task is, suppose a quantum state is randomly chosen from this ensemble and is supplied to Alice and Bob. Alice and Bob has to identify which particular state is given to them among the four one. This task is called local state discrimination task. And it was shown in this paper by Shivashish Ghosh et al. In Physical Review later that this is impossible by LOCC. This discriminating which state is given to Alice and Bob when Alice and Bob are spatially separated is impossible. Furthermore, it was shown by Shunshubra Bandyopadhyay and others that one if Alice and Bob share one bit of entanglement, it is both necessary and sufficient to accomplish this task. So given one bit of entanglement, Alice and Bob will be able to determine which particular quantum state from the four Bell state is given to them. Now let us consider the problem in our scenario. Suppose Alice and Bob is sharing one particular Bell state and they do not know which Bell state is they are sharing. For now, let's for the time being, let's consider that the shared state is 0 1 minus 1 0. That means this is B4 state. So they are sharing this B4 state, and using the same protocol that I have discussed earlier, that Alice will do identity on her part and Bob will do bit flip on her part, and vice versa. It is shown, it can be shown that after the operation, the state becomes like this. The mass state converts to L minus R, and the B4 state converts to B2 state. Now, note here that Charlie does not need to measure the mass configuration here. Here, only by running the protocol without Charlie's measurement, this transformation is possible. And furthermore, it can be shown that if starting from B1, this operation will give rise to B3, from B3 to B1, and if they were sharing B2, then the mass configuration goes to minus state and the shared state goes to B4. And if they were sharing B4, the mass configuration goes to B minus state and it goes to B2. So we have demonstrated this B4 going to minus B2 transformation here. Now, after the protocol has been run, Charlie will now measure the mass configuration in say in plus minus basis. So either he will get this or that. So once Alice and say now Charlie gets plus step. So it is sure after Charlie communicates his outcome to Alice and Bob that the shared state is either B3 or B1. And it is a well-known result from Walgett and Hardy that given two orthogonal multipartite state, it is always possible to discriminate which state is given to them. So they will be able to identify which state is given to them. So let's say B3 or B1. they will measure the correlation anti-correlation measurement. Alice will measure in 0 1 basis, Bob will measure 0 1 basis. If they say find that their outcomes are correlated, then it is B1. If it is anti-correlated, then it is B3. So this is the chart that they will implement to determine which of the which of the four quantum state is given to them. Now, one thing to notice here is that no new entanglement was generated in this process. So the start the game with one some entanglement between them, shared between them, and they did not need to generate extra entanglement to perform this local state discrimination task. This implies that indefinite causal structure as a resource is independent from entanglement. So it does not need to generate entanglement to be used as a resource. It is an independent resource by itself.
Hello, Pratik.
Yeah,
Sorry for interruption. Since we are running out of time, so
yeah,
we will
I'm
wrap
almost done.
in a few 2 or 3
Yeah,
minutes.
yeah, I'm almost done. Okay, so as I was saying that no new entanglement is generated, that marks the independency of indefinite causal structure as a resource. And one thing and another thing is that it is not always necessary for Alice and Bob to teleport the subsystem to accomplish non-local tasks. So this non-local task was accomplished without Alice or Bob teleporting any subsystem to the other lab. So this is an example where indefinite causal structure can be used as a non-local task. So before concluding, let's recapitulate what we have seen, that due to quantum matter, meaning matter that that requires quantum mechanical description, it is possible to generate indefinite causal structure. And this indefinite causal structure, or in particular indefinite causal order of two events, can be used as a universal resource for implementing non-local operations locally on C2 plus CD systems. Furthermore, in the last example, we have seen that indefinite causal structure is an independent resource of maximally entangled state for its function. Also, in our paper, we have conjectured and showed some results also, that it is possible to consider indefinite causal of order of d prime events, shows that this indefinite causal order of d prime events can be used as a universal resource for local implementation of non-local quantum operations on CD prime cross CD systems for d prime less than d. And as this is a this is a universal recourse, any non-local tasks are achievable using this resource. So thank you.
So, thank you, Pratik. It was a very nice, beautiful talk. So, the session is open for a quick question. Since we are running out of time, we cannot provide so much time. So, participants are requested to ask question if there is.
Mm. Can you hear me?
Yeah.
Okay. Could you please explain the meaning of causal structure
Oh,
in simple words?
oh, so so as I have mentioned that given two events, we can define the causal order between them. Causal structure is pertains to the space-time manifold. It basically indicates which event is causally related to which other set of events, and which set of events is causally disconnected from a set of events. So in a space-time, we have a collection of events. Now consider a particular subset of events. Now we ask the question, which other subset of events are causally related to this subset of events? This is determined by the causal structure of the spacetime. So for a given causal structure, we will be able to answer which particular subset of events are related to this particular subset of events. So the causal relations are basically well defined once we have the causal structure of the spacetime.
Thank you.
if there is no other question, we will move to our next talk. So thanks again, Pratik,
Oh,
for
thank you.
your beautiful talk. We are hoping to have you in next year.
Okay, thank you.